Hello. This is my repositories. Here is my bootloader. And I did crazy stuff here. Frequency shits, and here is my piano. So what we are going to do, let's break down the code which I wrote. Okay, I love this music. Let's do something here crazy. Rename. So let's first, I want to explain my paging mechanism here. I did some identity paging because I don't have to I don't use the MMU for page transformations like the complex things that trains MMU and I don't want my paging slower, and this makes paging transformations in the microseconds level. Yeah. Here control register 3. There are 1024 index here in a page table. I'm not going to teach you the x86 architecture, but I'm just showing how this works. Yeah, there are some kind of bits here, and it is dummy, not dummy, this is, let's say, it is reserved byte. Here is the PDE. What is PDA entry? First PDE entry, and a small stuff here. So I'm going to write ISRs. Print key and printing here. VGA driver. Okay. My ideology is making modern operating system more more easier to understand than ring 0, only because back in the MS-DOS days there are no protection between the hardware and the programmer. So you won't, if you won't destroy your own memory, the CPU will, the CPU is ready to for it, ready to do it for you. ASCII, is it? Hex, where is the hex? Okay, so this is the page file screen, so I will rewrite the ISRs here, and my paging is activated. Page tables. The identity mapping is really so fast. It does the mapping in a microseconds level, so it is the best optimization for my operating system for the 4 gigabytes of RAM, so I don't make a headache the paging, because Linux, Windows or macOS, macOS was ARM architecture, yeah, but it switched to x86. So the Linux, macOS, Windows uses the complicated way for they are in x86 64-bit mode, but I'm in x86 32-bit mode, because the 32-bit mode is much cleaner. Okay. Let's see what does give it us. Where is this bullshit? My old paging codes here. Let's see, and all the included data here. There are atomy function there. I forgot and deleted it. Oh, it's here. It's here. util.c. Oh, it's here, not deleted. Hell yeah. Where am I? Okay, that's nice. Char buffer. Wait. Wait, what the hell? Why did I do this here? Standard footage. C. I hate C. No. Modern systems are so creepy and bloated software as GNU Grub. I just use the GNU Grub is something more convenient. So anyway, there is much more bigger problem here. My isr.assembly, there is no log for logging which interrupt has been fired. So I will do a system here for in assembly for tracing which interrupt has been fired. There are so few interrupts here. I only handle 12 interrupts, but I should handle all interrupts here. So let's go. Let's read the manual and go. Which interrupts has error code. Simply, interrupt is, let's say, do you hear the phone when you have a message? This is an interrupt. Let's keep it simple. This is an interrupt. The interrupt at something comes and says the CPU I'm an interrupt, and there is a little embedded machine here prioritize interrupt numbers, interrupts according to their numbers. It gives numbers to interrupts and it pushes the CPU which interrupt has been fired. Okay, there are 20 interrupts here, and I should all 20 interrupts here. I should quit. What did I change here? No. Okay. Let's see. IDT, and there is a table that holds the numbers of interrupts. Handle int.c in services.c. okay. isr.assembly. I don't like writing ASM instead of assembly. Wait, what do I have? In services.c. No. Okay. So I will delete all code here and let's go. ISR extern void which sorry, let's note here somewhere. Note it somewhere to not forgetting. Yeah. Ama tamamlayalım. Ha? Tamamlayalım. önem bakın. Okay, which are remaining? 1, 2, 3, 4, 5, 6, 7, 8. Seven, 8, 9, 10, 12, 20. There are 20 interrupts here, and some of them push the error code to the stack. Wait. So I don't have to implement this interrupt because it is reserved. So what does the reserved interrupt do? Nothing. Okay. And ninth interrupt is not needed because it is reserved to virtualization exception x86 FPU maskable, and there are maskable interrupts and non-maskable interrupts. The maskable interrupts are let's keep it simple and say maskable interrupts are wait, there is one here. Maskable interrupts are something that can be shut down by CLI instructions, and non-maskables are very critical interrupts that system can't run without it, like IRQ1, the interrupt descriptor table 8th entry without remapping. External ISR 5 void external ISR 7 void 10 void external void ISR 10 ISR 16 void ISR external void 16 and 17. And if an critical interrupt occurs, for example page fault, and not page fault can be recovered. Let's say double fault is not cannot be repaired because it is a critical interrupt that can shut down all system. Interrupt descriptor table 8th entry. void ISR void. And there is a vector here. I did mention here, if a vector number is smaller than 21, it goes through trap, but if it is bigger than it will go through interrupt. And there are initialization command word 1. There are documentation of this in the Intel manual for BIOS or system programmers manual, the serial peripheral interface. Wait, it's not vector number for it. It's 2. That's because I don't go to, there are wait, okay, there are a programmable interval timer and PC speaker. A PC speaker is something that sends raw bytes to the speaker rawly. I use it for my kernel because people get fucked with more advanced ones. I stay in retro one because my ideology is bringing back the MS-DOS and Commodore 64 or other legendary computers. It's called Advanced Programmable Interval Timer. And more modern versions of programmable interval timers. Interrupt timer, or what the fuck was it? Set date. Seven, 10. People often call me mad, or they say me meta AI, but what the fuck, bro? I did an operating system. How can you call me meta AI for creating meaningless photos several times? How can it be possible? In a school, people call me meta AA. What the fuck, bro? Because they are in Surface. They are in Surface. It is easy to say because they don't understand what the operating system developers do here. They only program in Python, JavaScript, or any other fucking languages. Anyway, clone languages. Man, who care about JavaScript in the 2026? Who cares about JavaScript, Python? Okay, so let's void here. Man, how can it be possible to void type don't have any size, unknown size? How can it be possible? You C makers, C language makers, classic C programming shits. Anyway, let's do our assembly here. People should call code in assembly, because assembly is widely used in the world. All the systems are written in assembly, not in Python, because assembly has external power. You can control anything with assembly, because assembly gives you full control over hardware. Anyway, let's do globals here. Global, wait. The setGate functions sets the IDT's vectors, passes the vector numbers in hexadecimal to IDT vectors. IDT vectors are here, and there are some bitwise operations, segment selector and handler's address here. Like IDT wants from us a 16-bit, a 2-byte offset low, and 0 something here for giving a general protection fault, and not much things. Always keep the system simple. Yeah, I don't like the global things. What the hell is this? I just spent most of code for declaring a global variable. Anyway, this is the best way to do your own assembler. The West way was Terry Davis' way, because he made everything. I don't believe in an assembler, because most of assemblers are bloated software. ISR0. Okay. Interrupt here, and let's say global. What does this do here? ISR 0 push up. Let's keep the registers in the stack. Int services.h handle int handle db handle the user should be aware what the hell is going on system. Handle division error. Handle de void. Let's die the kernel, make the kernel to die screen, print 0 division, 0 division, kernel panic, ASM volatile, clear all interrupts, and ASM volatile hold. There will be no interrupts coming, and the processor will wait till interrupts coming, but interrupts won't come. Okay, handle division error. So handle division error void call extern. Wait, I have to extern global. Extern handle de call handle de, and I have to declare a instruction pointer here, because I will add instruction pointer for tracing where the code went. Okay, unsigned 32-bit instruction pointer here. Now it will give error. R. The EIPR will be extern handle D, extern EIPR. R means register. And for page fold, I will add the page fold. EIPR handle DE call handle it will return, and I push all registers to the stack, and it will, when it will return, it should there are no address for going, so it will wait till the processor. Okay, anyway, push at, pop at, interrupt return, debird. Well, let's talk about when an interrupt occurs, what happens. So when an interrupt occurs, the CPU push the all registers to the stack, like specific registers, not all registers. The 32-bit registers are pushed by us, but the instruction pointer code segment register, E-flags register, is push the stack by the CPU, not from our perspective. The CPU push the stack itself. The CPUs are so smart. Reserved instruction, so I don't have to use the reserved instruction, because why should I handle an reserved instruction? It will take one line of code in my kernel. Okay, there is reserved instruction and non-maskable interrupt, non-maskable external interrupt. Okay, I won't handle it because it is an interrupt. It is IBM's mistake. The interrupts are in this interval, like 32 to 255. They are all interrupts. Okay. Next is breakpoint. Breakpoint is a trap, no error code. And what the fuck is breakpoint? External handle BP. Handle common. Handle let's make the kernel die. There is a good thing in x86-64. There is an you can reach the instruction pointer by just writing code like this. REX, let's say REP. This is called RIP relative address. RIP relative, instruction pointer relative address. But if you do a declaration like dereference like that, your RIP's showing opcodes will go through REX register. This is the most I liked things in x86 64-bit mode. Handle base breakpoint, handle overflow. This is an overflow. When an overflow occurs, the overflow flag is set in E-flags register. Overflow. What is the overflow? Oh, I have to do things here. Push out. There is no calling conventions or any other shits here, so I can basically say keyword EIP register ESP, because the stack pointer currently shows the return instruction pointer. Okay, it will load to my declared variable, which is the number of overflow is 4, ISR 4. Push at wait, I have to do this here global, because everything will be shitted. Okay, handle by screen print breakpoint okay, return. I don't know what does breakpoint does, but I will read about it. Boundary range pixel. Oh, the halt instructions basically halts the computer. Okay, when the clean instruction is executed, the interrupt flag in eFlags register is went to 0, and the processor will wait till when an interrupt occurs. The CPU will go to handle this interrupt, but when I set the clean instruction, the interrupts won't come, and the processor will wait till interrupts till infinity. And halt instruction is halt instruction saves the battery. Okay, overflow, bound range, VR, void, ISR 4. What was the ISR 4? Overflow. The eFlags is, and when I say this like this, the assembler will will be dumb and regard it as a eFlags register for real. E flags R, and the so this text is currently points to instruction pointer. Above instruction pointer, the code segment register is there, and above the code segment the E flags register. So I will add 4 for code segment and 8. And move keyboard pop-hat. Wait. That's not showing it. No, it's not saving. Okay. Pop up. Simply do. Wait. Okay. So when I execute the push-out instruction, the CPU currently shows points to the ESP itself. It points to itself. Okay. ISR 5. Was there ISR 5 here? Yes. What is the ISR 5? Stands for boundary exceed. Okay, let's simply dice screen here, and dice screen here. Bound. Invalid opcode. There is an invalid opcode handler, I think, here. Abort. No PV, no double fold. Machine check here. And there is no invalid opcode handler. Oh, wait. I have an idea. Making it case one, just print. Oh, that is a great idea. That's a great idea. Very great idea. Where come I here? So, if I see my it's a great idea, but will it I will try to implement after the video. Okay. My idea is this. Handle all interrupts. Okay. There is an interrupt number holder. It will basically switch cases. Holder, case 1, dice screen, assembly volatile, clear all interrupts, print. What is the first interrupt here? Divide error, division error, let's say mathematical error. And a little information here for the user. Check instruction pointer. Okay. From now, the user will be convenient with what interrupt has been fired. Okay, switch and cases. Simple, very simple. Case 2. Okay, what is the second interrupt here? Reserved. Let's go through 4. Overflow. No, close this. And die screen here. Oh. Breakpoint. Okay. Then case 4. Which is a force interrupt overflow. Okay. Always keep your code clean. Overflow. Check instruction pointer and flag register. E flags. Extended flags. Then case 5. And don't forget that the cases are working on light speed. They all are faster than if else, because in a way bound exceed check instruction pointer basically. Okay, and case 6 die screen. This is very basic. This is an amazing idea. Invalid code. Okay, invalid code, my favorite exception here. I don't know why. Invalid opcode. Invalid opcode. Write good code. Check. Case 7. Device not available. Case 7. Device not available. Here, copy paste. Just copy paste. Wait. Device not available. There is no need. Check your device. will basically do all things here. Lining. Okay, 7, 8, 9, 10. Okay, 10 and okay, 7, 8, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Oh, what the? Wait. Okay, 8, 9, 10, 20, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And the 5 interrupts here are reserved. I have to delete the 5 interrupts. Case 7, case 12. Whoever watches how. I have been doing calisthenics for about I have been doing calisthenics from August till now. I have 1 year in gym and about August, September, October, November, December, February, January, February, March. I have 8 months. I have 8 months. That's really, I have 8 months. Yeah, I have experience about 8 months. I have been doing calisthenics for 8 months, and I can do iron cross, front level, handstand, Azarian cross, and back lever and muscle ups. I have skills that they are very important for tendons, health, and general health. I'm about to be professional because the iron cross and Azarian cross are not kid exercises. They are not kids exercises. They are elite level things. Wait. Epic. Yeah. Highest. Yeah, this is simultaneous exceptions and interrupts. Priority. The priority, the highest is hardware. Machine check. I said you they are highly priority interrupts. The init interrupt, flash, they are cache things, caching mechanism. There is a trap gate, interrupt gate. As you can see, interrupt gate affects to interrupt. The interrupt gate is affected by interrupt flag in the e-flags register, and trap gate does not change any flag, interrupt flag. Okay, so let's talk about a little more paging. Most people come and say, You don't even do any shit here, paging here, but if you think I am mapping 4 megabyte paging, I am using 4 megabyte paging with page size equals to 1, and CR2 register holds the page fault address, linear address. And if you think what happens if I try to multiplicate the 2 to the power 10 to the power 2, what happens? It does this number. Yeah, that is the megabytes of where the page directory entry. A page directory entry has 1024 entries. If you multiplicate the entries to the 4 megabyte, you can get the 4 gigabytes. The 4 gigabyte is something you can reach to the maximum level of address. The 4 gigabyte is the maximum address you can reach in x86 32-bit mode. So there are entries. I did 2 different structures for physical address and page directory. Oh, while one. The C language says you can use the while without braces if you have only one line of code under a while loop. So I'm implementing this here. Dennis Ritchie man said it. Kernighan someone said it. And let's listen their words and implement their words in real life. The C programming language is one of the greatest languages here, but my language will be the best. What was the 8th interrupt? Double fold. Yeah, double fold. Double fold. I love double fold. Double fold. Triple kill. Double kill. Double fold. Double fold. Kernel panic. Kernel panic. The Linux kernel panic. The Linux has kernel panic mechanism, and they use that VGA text mode in kernel panic mechanism because they don't have Wayland or something similar to Wayland shit, because you have to initialize the GPU complex awful things. Just use MS-DOS. MS-DOS is the greatest operating system created by Tim Patterson. Tim Patterson first made the quick and dirty operating system, and Bill Gates come, and for the IBM he promised that IBM will have IBM was trying to go trying to have the best computers in the world, and Bill Gates just give the license to IBM. The first wanted to make the quick and dirty OS to Gary Kildall, which the first used the BIOS word. The BIOS word is came to computer science by Gary Kildall. He was CPM, like he did CPM systems, a virtualization exception here. Oh, the machine check exception is a critic exception that it's a hardware fault. Check your hardware. Check hardware. Okay. It would be nice when I do it on the center. Alignment check. A few faults. Do not do mathematical get a math lesson, because normal person knows that there is no zero division in the math, because how can you divide your number to the void? Page fault. A non-paged area. Check CR2 register. General protection mode fault. stack segment fault. Segment not present. Okay, I will do the format specifier print when I write a VGA driver, because I think VGA driver is a bit more cozy. What the fuck? Damn.
Of this man. This is the point, because it doesn't fucking matter. All of your tech track should not be read of C#. That's what being software engineer.
What the hell is it?
Movies.
Functionality to support age verification into their init script.
Yeah, Linux is bloatware, but more good bloatware from Windows. It is a Linux Droid Volts.
Linus, do you follow any development of any new programming languages? Do you see any language except C which is suitable for development of operating system?
I have yet to see a language that comes even close to C in that respect. It's not just that C, you can use C to generate good code for hardware, it's that if you think like a computer, writing C actually makes sense. So when I read C, I know what the assembly language will look like. And that is something I care about. The normal
Derivative of 2 of x.
It is easy. 2x.
Isn't that just 2x? That is correct!
Hey, the calculus is one of the hardest. Calculus and vectors. I love vectors too. There are magnitude of vector and lengths of vector. These are the same things, but if you want to find the length of vector, you just simply do this formula here. Wait, what the fuck? Undo everything. Okay, the adding vectors, the square root, a sigma here goes n-1, and here is a vector I to the square. Okay, what is this? This is length of vector, or just say magnitude of vector. The two things are same, but if you want to find the actual length of vector, you use this. The vectors can be multidimensional, and for two-dimensional for us for calculating the hypotenuse of circle. Any place. Wait. This is 90 degrees here. Here. This is simply a vector. Let's say v1, v2, and this is called v3. Okay, is equal to in square root v1 square v1 v2 square plus vn square vn plus 1, and this go to infinity. Yeah, this is what does this look like, and let's calculate the hypotenuse of hypotenuse. This is great. The hypotenuse will be equal to v2 square and v1 square. It is, let's say it is 3, 4 and 5. This is a Pythagorean triad, simply. Will be 5. Okay, so when I want to, there are three-dimensional vectors too. Three-dimensional vectors. This is where we are in. We are in three-dimensional. It is z here. The height is the y here, and there are x. It is three-dimensional. We are in three-dimensional. Here we have height, we have length, and we have mind. The vector here, it has a terminal point and starting point. The starting point, let's say, is P, and terminal point is Q. If you want to calculate this vector's length, you just simply get their coordinates here. Let's say P's coordinates are equal to 0, 0, it is 0, let's say 1 here, and Q is equal to, let's say 5. X comes first, 0, y is let's say 9, and z is 5. So let's say this is I here, J and K. You have to know the algebra well for multiplication of vectors. So when you multiplicate a vector, you simply, let's say u constant here, u will be multiplied by 0, 0 and 1. If you put u here, the u will be multiplied by 0, 9 and 5, and you find the vectors just like this. Find the lengths of vectors. Will be wait, magnitude of 3. I plus I multiplied by z here in our 1 plus x multiplied by j here 0, and the rk will be multiplied by 1, and you will add them. Okay, so I show how to multiply vectors and basic vector things. Let's go through in operating system development. Yeah, which is it? Invalid TSS. Invalid TSS. Check task register. I have very good muscles, but my generation is a little bit slow. Coprocessor segment overrun. Result. Okay, let's go through in assembly. Oh wait, what's wait, what? Die screen. Oh. Wait. Oh, yeah. Dice screen is here. Oh, shit. Oh, okay. I implemented the dice screen in assembly because assembly does not add compiler things like epilogue, prologue. Let's go through in assembly. ISRs. Okay, ISR 5. What is ISR 5? I don't have to extern all things here. Extern only, handle all interrupts. It is software interrupts here. ISR 5. The assembly must be written in caps lock because assembly is not a language. Assembly is hardware. Assembly is CPU. Okay. Push 0, the word 0. Handle DE. Add. Wait, not add. Move keyword holder here. Holder. Handle interrupts holder. Move keyword holder to current ESP and call handle DE. Okay, so yeah, the instruction pointer points to error code. Instruction pointer without error code. ESP shows the instruction pointer. We have to add instruction pointer 8 to reach to E flags register. EIPR if flags are handle all interrupts. Did I do all things right? So in x86 32-bit mode, you have to use 32-bit width because your stack is 32-bit aligned. So if you push a word here, your CPU will waste extra CPU clocks, tacts, for aligning this shit for you, and your word will become the word, and I don't want to make CPU work more because it can handle it by one tact. So if you thus the CPU will waste more time for aligning word or byte, because in x86 32-bit architecture we are using the 4-bit aligning, and this is why I push the D word to the stack. So don't forget the push here, pop here after the push. if you want to what happening behind the assembly, you just simply you will go and study electrical engineering, because electrical engineering is something you get more advanced. You explode, your brain becomes explosive after the math, after the transformations, vectors, algebra, linear algebra, matrices, and so on. You will learn there how the what the hell was you saying? Transistors. You will learn how transistors work. It's a fault in Bible code. Okay, our error code start from the from double fold and continues through page fold, and there is only alignment check after the page fold with error code. We'll continue one and divert, move divert, instruction pointer or ESP, and I have to be more attentive when I get error code in the stack, because if I align the stack wrongly, my code will jump to the junk code, like it will get there, it will get invalid opcodes here, there. Call interrupts are very good things to learn assembly. Okay. Okay, there is a error code in the stack currently. That's why I added additional 4 to the stack pointer for reaching the stack pointer instruction pointer correctly, the faulting instruction pointer. Okay. The stack pointer shows to the error code, and above the error code there is my instruction pointer, and I pushed something error code. There will be a holder here and my error code, and add ESP additional 4 and return from interrupt ISR 9. This is ISR 9. Oh, it's reserved 10. Instruction pointer, error code, instruction pointer, bird, code segment 8, code segment 13. In x86 architecture, the software programmer must be very attentive, because x86 architecture is complex instruction set architecture, and the arithmetic logical unit and the flags are flags. Let's say this is flags and this is let's say this is flags and this is arithmetic logical unit. It is a unit in the CPU, and the arithmetic logical unit and the flags are connected. If you add or subtract or do any arithmetic you just change some flags in the eFlags register. For example, if you do arithmetic right, shift arithmetic right, the out bit, which is, let's say 1, let's say you have number 2, and you shift left, and your 0 flag, if I don't remember wrong. Your zero flag will be set the bit which is out. You basically divide to power of 2 when you shift right, and shift left is something you multiply. Let's say you shifted the number 2 to the right by 1. It divide 2 to the 2 and you will get one number 1. And if you shift right the number 1, your out bit will be set to the 0 flag. And this is why the x86 architecture, in x86 architecture, the programmer must be very attentive. Okay, pop the word, add ESP4 and interrupt return. I'm right. Let's eat some banana. Whoa. The aborts are something you cannot return. Okay. Oh. Really? Am I doing the stream for 2 hours. Whoa. Cool. Hey, do you guys know why I'm here? And this I should look like shit. I have a book that I love it for calculus. That's called Thomas Calculus. Calculus. Yeah, this book. It is a Bible of math, I think, because it has huge numbers and huge numbers of things. It is derivative. LNX. Yeah, and this show is something that I know that I love in this book is it gives solutions, theorems, and what was it named? Proof. Yeah, proof. It gives proof of everything you see in this book. It is derivative. For example, it starts from basic to advanced ones, like things look like things like it. I love advanced things. This is limit here, and this is integral here, the UE plus C. Yeah, I know this. I know integrals like basics. I haven't do integrals for 1 year. The second here. Oh, I can do it. This is proper integral. This is called proper integrals. Wait, I know the basic integrals. Where is integrals? The integral starts from here. Integrals. Thomas calculated a great achievement of clearing. The Archimede made the integral. The integral simply adds the integral is the is a summa of particles that cannot be added by a human. Like we cannot add the infinitive particles in the interval. Yeah, this is the definition of integral. Anyway, I'm going to have bath and sleeping. Anyway, goodbye. I have a problem, like I cannot multiply the numbers, basic numbers. I have very strong wrists. Anyway,